In this lecture, we concretely define this Q sub P. So you see that this AI you pick up from 0 to P minus 1, and any element of this Q sub P, it actually looks like a series like this. So you have this P, that is the prime P in the denominator, and then you have this constant term here, and then A1 times P, A2 times P square, and so on. So this should remind you of series from complex analysis. Now Z sub P, these p-adic integers, these are set of all numbers of this Q sub P whose p-adic expansion does not have negative powers of P. So this portion is our p-adic integers. So what are the units of this? So the units of this are precisely those integers, those p-adic integers whose first digit is non-zero. So this has to be non-zero. So notice that if you have a p-adic integer, you could have everything here as 0, and you could start as a2 p square and so on, but then it will not be a unit. So for it to be a unit, it has to start as a0. So it has to start right here. So again, all these coefficients are from 0 to p minus 1. So in particular, this a0 is not divisible by p because it lies in this these many numbers. So our first lemma. So ring of p-adic integers, the ZP which we have just described, this is an integral domain. So this you can see easily. If a times b is 0, this both a and b are here, then you take its valuation, that will also be 0. So this, because of a multiplicative property of this value, this will go like this. So this is our p-adic absolute value. So either this is 0 or the second term is 0. So that would mean that either a is 0 or b is 0. So this ring of p-adic integers is an integral domain. So we can construct this algebraically, because since a z sub p, these p-adic integers, they form an integral domain, we can construct its ring of fractions. And you can call this ring of fractions as p-adic rational numbers. So again, you can say that looks like d over q, where d and q are in z sub p and q is not 0. So this is a better way of thinking of it, but here you can think of this too, but you have to do division, and we have seen the division process before algorithmically via an example. So this was done in a previous lecture we have done addition, multiplication, subtraction, and division in this Q sub P. Analytically also you can construct this Q sub P, that is field of p-adic rational numbers. So this is nothing but completion of rationals with respect to this this p-adic absolute value. So just like real numbers is a completion of rationals with respect to absolute value. So just standard absolute value, you take rationals, you complete them, you get real numbers. You take this p-adic norm, you will get QP. So real numbers are complete, rationals are not complete. Completion means that if you take a Cauchy sequence with respect to some kind of a absolute value, then it has to converge to an element of that field itself. So if you take a Cauchy sequence in real numbers, take absolute value, every Cauchy sequence will converge to a real number. But it is no longer true for rationals. So it could converge to numbers like square root of 2, which are not rational. So once you construct completion, you get real numbers. Here you construct completion with respect to this, you get this Q sub P. So again, recall this order sub P is just the p-adic valuation. This is p-adic valuation as defined in this lecture on discrete valuation rings. We also denote it as this V sub P. And recall associated absolute p-adic value is this. So this is our absolute p-adic value. So this is order of A. If you are forgotten it, just recall this example. This order of p to the n is just n, and then if you take its absolute value, this is 1 over pn, just like here. So instead of a, we are writing p to the n. So so these notions were defined on p-adic integers, and they canonically come to our rationals, that is our p-adic rationals. So that is order of this d over q is order of d minus order of q, and d over q, this p is this. So this is just from the definition. So this, if you see as a metric, you see the sequence, this p, p square, p cube, and so on. So if you evaluate p, this is 1 over pn. So as n goes to infinity, this will go to 0. So this sequence converges to 0 in this p-adic rationals. So we have described this ZP before as these terms. You can also see it as this all this a in rational such that this a sub p is less than equal to 1. So this has to be less than equal to 1 because we are talking about ZP, these terms. All these terms have p in the numerator. So once you take order like this will become 1 over p to some power, and therefore this will be less than 1. So this is called closed unique p-adic disk. Now units, we are calling this as first digit is non-zero. So if you take valuation of this is just going to be p to the power of 0, so just give you 1 because this is not divisible by p. So the order is just going to be 0. So p to the order would be 1 over p to the 0 will give you 1. So this will give you p-adic circle because this first term is non-zero. And all other terms which are less than 1, which is all these terms which have a factor p, they form the maximal ideal. So and this will be, this maximal ideal is often called the open unit p-adic disk. So this unit just corresponds to this one here, and this unit corresponds to the units of the ring here.